Okay, good afternoon. Welcome. Today is 2 square, 3 square, 5 square. I know students in the lab got that. All right, let's continue with our discussion of semiconductors and then fundamentals, and then I will go over the homework problem at the end, the last 15 minutes. Okay. Okay, so where is the notebook? Oh, I'm already on the notebook. Okay, so we stopped here last class. We were talking about donor ionization and intrinsic carriers, and how the introduction of external dopant impurities can change the properties of a semiconductor, right? So this graph here just shows you the relationship between the extrinsic dopants and the intrinsically generated charge carriers. So on the right here, we have the intrinsic range that is at very high temperatures. This is greater than 500 Kelvin, 500 K. Room temperature is somewhere over here, which would be, actually, sorry, room temperature is 300 degrees. So this right here is freezing, 0 degrees C, 273 Kelvin, right? 0 degrees C. Now, here, of course, is the freeze out. Freeze out means it's not enough thermal energy, no bonds are broken, there are no free charge carriers due to thermal carrier generation. Okay, hence it's known as the freeze out range. Now, here is where the magic of semiconductor happens. The level of dopants required to actually create or overcome the intrinsically generated carriers is at least 10 raised to 14, 10 raised to 16. Okay, so at 10 raised to 16, the extrinsic carriers overpower, well, not overpower, but are far larger than the quantities of the intrinsically generated carriers. Okay, and that holds true all the way until, I would say, about 550. Okay, but beyond 550 Kelvin, interesting phenomenon occurs, and the extra thermal energy beyond 550 K allows a whole lot more electrons to break their bonds and become free charge carriers. So from that point on, the intrinsically generated carriers will now number in huge quantities, and they will be far larger than the externally introduced dopants. Okay, and so that's what this chart indicates. Right here in the middle, you have the doping. So beyond 550 K, the number of intrinsic carriers will be far larger than the doped material. Okay. Ni in general refers to the number of charge carriers that are present in an intrinsic material. The I stands for intrinsic, meaning it's generated solely due to the thermal energy. And Ni is also equal to N, also equal to P. N in this case represents the number of electrons. The P represents the number of holes. Okay, so it sometimes gets confusing. Ni is representing both electrons and holes. If it's just N without any subscript, then it's electrons. And if it's P, then it's number of holes. And then we'll see in just a couple more slides that this N can have two other subscripts, which is N and P. This P also can have a subscript of N or P. Okay, but if you see I as a subscript, Ni simply refers to the number of charge carriers. It is equal to the number of electrons, and it's equal to the number of holes. Intrinsic charge carriers are generated due to thermal energy. So a electron moves out of its spot, and at the same time, a hole is also created. Hence, N is always equal to P for intrinsic. Okay. Electron acquires sufficient thermal energy, breaks its bond, moves out of its spot. When it moves out of its spot, leaves behind a hole. So every time an electron is generated, a free hole is also generated. So N always equals P. N always equals Ni. Okay, so let's get to the next slide. So now we have extrinsic semiconductors, right? So we have N-type material, we have P-type material. In an N-type material, we have a plethora of donor atoms. So Nd, these atoms will donate one extra electron. And so on the left side here, you see these dots represent electrons, and the circles represents holes. The squares represent atoms. And so this square with a plus sign is noting that it's a donor atom. It donated an electron, so it now has one extra positive charge. So this is Nd. And on this side, it's the exact same thing, square with a negative charge. Acceptor atom, it accepts an electron, so it has one extra negative charge. So it's N-type material and P-type material because it has an excess of electrons and an excess of holes. Let's take 10-second pause. Let me know if you have any questions. Okay. Any questions? Okay. So N-type material, what makes it an N-type material? Right, we take donor atoms. Intrinsic level is around 10 raised to 10 free charge carriers. Number of donor atoms would be at least 10 raised to 14, 10 raised to 16, 10 raised to 18. So let's say we introduced 10 raised to 16 numbers of atoms in volume of centimeter cube. That number is sufficient to overcome all the intrinsically generated charge carriers. So the intrinsically generated electrons and holes number 10 raised to 10. The external electrons are now 10 raised to 16, far larger number than the intrinsic numbers. So if the number of electrons, the number of negative charges outnumbers the number of positive charges, positive charge carriers, it's N-type material. And the opposite is true for the P-type material. We have number of holes that are available in far larger numbers than the number of electrons. Then it's a P-type material. Overall, the charge remains electrically neutral because every electron that is donated, you have an extra positive charge in the donor atom. So overall, the charges are neutral. The same thing happens here. An acceptor atom accepts electrons, so it now has one negative charge, but then it leaves behind a positive charge in the other place. And so overall, the electrical charge is neutral. The total number of electrons in an N-type material can said to be approximately equal to the total number of donor atoms, because Nd is far larger than the number of intrinsic carriers. So Nd would be 10 raised to 16, 10 raised to 17, 10 raised to 18. The intrinsic electrons will be 10 raised to 10, 10 raised to 11 perhaps, not far more than that. So the total number of electrons in an n-type material comes from the intrinsic thermal generation as well as the extrinsic or external doping. The external doping is far greater in numbers than the intrinsic carriers that we can say that the total number of electrons would be approximately equal to ND. And many times for many use cases, we use this relationship for our calculations. And same thing occurs on the P side, where the total number of holes would be approximately equal to the total number of acceptor atoms. All right. So far, so good. Any questions? Yes. So NC and NV is the number of states that the electron can occupy in the conduction band and the valence band. And that equation we saw earlier in, let's see, in this slide right here, the intrinsic carrier concentrations. We have this equation, the root of NCNV e raised to EG over KT. So the density of states in the conduction band, the density of states in the valence band. Those are the discrete energy levels that an electron can occupy in it. It's actually a very important concept in quantum physics, and we use those to derive our equations for solid state physics. Okay, that question leads me into this equation, right? We just saw in the previous equation, square root of NC and V. So in an N-type material, holes are far less in number. So P can be approximately given by this equation. Take the previous equation, root of NC and V, and divided by the total number of electrons, which is basically the number of donor atoms. And on the P side, electrons are far less in number. And so it can approximately be given by the equation divided by the number of acceptor atoms, Na. NC, NV over Na, and NC, NV over Nd. Okay, yes. No, that's the number of, excuse me, sorry. That's the number of states. So that's the density, that's known as the density of states. That's the number of states an electron can occupy, or the number of energy levels or states that an electron can occupy while jumping from the conduction band or the valence band. Oh, so okay, I see what you're saying. So question being asked is why are we using capital N for, multiple things? And it happens all the time. There's only so many alphabets to go around that we use the same alphabets for multiple different things. And sometimes you also have like lowercase letter means something else and uppercase letter means something else. As an example, what is the notation for current? We would think it's an important quantity, so the current would be given by C, but current is given by I. What is C used for? Coulombs also. Capacitor, speed of light, lowercase c is something else, uppercase c is something else. So oftentimes we have these, confusing things. We need context to make sense of what is actually being referred to. So NC and NV are the number of states, ND and NA are the number of atoms. But in both cases, the N indicates the total number. That's a total number of something. Okay. Okay. So the keyword I used here was there's an excess of one kind of charge carrier in each material. So if it's an excess, they are present in the majority, hence they are known as the majority carriers. So in an N-type material, the majority carriers are electrons, and in a P-type material, the majority carriers are holes. At the same time, the charge carriers that are present in lower numbers is known as the minority carriers. So electrons and holes, and P-type, we have holes and we have electrons. So we have majority and minority carriers on both sides. Now, I will come back to this after we finish all of the slides, because this also relates to how we're going to apply this for that homework problem. Okay. All right. One other thing about notations. Here I stated, previous slide I stated, right? Ni, the subscript I, is simply for intrinsic carriers. So Ni represents both electrons. It also represents holes. Okay, it's simply the number of charge carriers. Because the holes are created when an electron breaks a bond and moves out of its spot. So every time a free electron is generated, a positive hole is also generated intrinsically, thermal generation. We cannot have a hole created without an electron being generated, right? So a free electron generated by its breaking its bond, it also generates a positive hole at the exact same time. So they always go together, they always go hand in hand. Hence, they are known as electron hole pairs. Electron hole pairs. And that process is known as generation. This is a very important process. So every time electron acquires thermal energy, breaks its bond, generates an electron hole pair. Every time there's an empty spot, an electron could acquire or drop or lose energy and drop into that empty spot. When an electron drops into that empty spot, that process is known as recombination. Okay. So you have generation and you have recombination. So every time an electron jumps into an empty spot, it recombines with the hole, and the negative and the positive charges disappear. Okay. The negative and positive charges disappear. That makes sense? So this process, that is generation, creates electron hole pairs. And then you have recombination. The generation is the separation of electrons and holes. Recombination is the combination or combining electrons and holes. And this is going to be important when I come back and explain what it means. Not what it means, the homework problem. Okay. So generation and recombination are important processes. And one more point about that is it is occurring constantly. It's occurring constantly. If I take a piece of silicon, you remember I brought those wafers in during class that day last week. So even if you have that as room temperature, there are electrons that have acquired sufficient energy because of this room temperature, right? Almost 300 Kelvin. So those electrons are constantly breaking their bonds, becoming free carriers, and within its lifetime, it's again going and recombining. So the process of generation and recombination is balanced out. It's constantly occurring all the time. Okay, constantly occurring. And put a pin in that, and we'll come back to it later in this class. All right, so we looked at that. And doped semiconductor materials. Okay, so in general, donor atoms are donating electrons. So they are losing electrons, right? So they are creating more electrons when you introduce them in a semiconductor material. Acceptor atoms are going to accept electrons, hence they are creating more holes in the semiconductor material. So this gives us p-type, and this gives us an n-type semiconductor. Okay, p-type and n-type semiconductor. Oftentimes, or not oftentimes, sometimes for special use case, a semiconductor material will have an equal number of donor and acceptor atoms. And so what that does is it creates an almost equal number of electrons and holes. Okay, so it behaves like an intrinsic semiconductor. And the name for this special type of semiconductor is compensated semiconductor, known as compensation. Again, if you introduce donor atoms, it creates an n-type material. If you introduce acceptor atoms, it creates p-type material. But if you introduce both in equal numbers, we get what is known as a compensated semiconductor. And it behaves almost like an intrinsic semiconductor. So then that begs the question, why would we do something like that? Well, the answer is for control. Intrinsic semiconductors, as I stated earlier, are not very useful. The way they are created or the way they are found is not very useful in its natural state. Okay. Excuse me. We can neither use them as a conductor, nor can we use them as a good insulator. But if we introduced a whole lot more extra charge carriers in there, now these charge carriers, even though they are in equal numbers or almost equal numbers, we can control the flow or the movement of these charge carriers. If the number is low, no matter however much voltage we apply, we cannot accurately or very precisely control the movement of those carriers in an intrinsic material. But if you have a whole lot more charge carriers present in there, we can now control how they move in response to reasonable electric fields. And so one of the applications for these kind of semiconductors is in low conductivity devices, right? So charge carriers are present in positive and negative charge carriers are present in the same semiconductor. And so we can use them for low conductivity devices. That's a compensated semiconductor. But that's as far as we're going to talk about that. All right. So N-type material and P-type material. Let's tackle N-type first. N-type, we stated that we introduced donor atoms. So Nd, the number of donor atoms, is not equal to 0, right? Nd is not equal to 0. At the same time, if it's a 100% pure semiconductor device, there would not be any acceptor atom. But in real life, that's not possible. So in real life, even if you have an N-type material, there is a possibility that there are acceptor atoms present in the device. This could be intentional or unintentional. Okay, could be intentional or unintentional. So the number of acceptor atoms is also non-zero, which is the second point. So the most important criteria to create a N-type material is that the number of donor atoms must be far, far greater than the number of acceptor atoms, meaning Nd must be far greater than Na. Sorry, Nd must be far greater than Na. And the difference between the two must be large enough or far, far greater than the intrinsically generated carriers. Okay. If Na is 0, then it's just Nd must be far, far greater than Ni. But because Na will cancel out Nd or some bit of Nd, then the difference between Nd and Na must be far, far greater than Ni. All right. And the same thing for a p-type material, except in a p-type material, Na is available in far greater quantities and Nd would be very small. So Na must be far greater than Nd. And for it to be considered a p-type material, Na minus Nd must be far, far greater than Ni. So here, Na minus Nd must be far, far greater than Ni. All right, let's take a pause, think over all of that, and let me know if you have any questions. All good? Okay. All right. So what constitutes a good doping profile? Well, intrinsically generated carriers are around 10 raised to 10, approximately 10 raised to 10 for silicon, right? So sometimes depending on the environment, it could be 10 raised to 11, maybe even 10 raised to 12, which is very rare, but around 10 raised to 10. So depending on the temperature, the intrinsic numbers keep on increasing. Lowest number that can be considered to be good enough is 10 raised to 14. So if you introduce external impurities, the dosage must be 10 raised to 14 atoms per centimeter cube. So all of these numbers, excuse me, all of these numbers are either the number of atoms or the number of electrons or the number of holes per centimeter cube. That's why these numbers are kind of insanely large. That's the way industry has been. When I first started learning about these, I was like, why are we doing this? When everything else is worked in microns, why do we need to use 10 raised to 18, 10 raised to 19? But that's the way the industry has evolved. So we're just doing that. But as an engineer, if you're performing any calculations, again, if it's in centimeters, you need to convert it to meters. If it's microns, again, you convert meters. So whenever you plug your equation, whenever you plug your numbers into the equations, you need to be careful that you are converting every unit and every unit prefix. Okay, otherwise you'll end up with the incorrect answer. Okay. As the doping concentration keeps on increasing, yes. So the question being asked is, how does it affect the purity of silicon? It depends on how much area we are using. So are we the specific answer to that question would be, what specific part of the device are we talking? Are we just talking in the region that we implanted? I mean, it's still silicon. And the answer, as you stated, yeah, it could be above 99%. Yeah, 99.9% or so. Because the number of silicon atoms in there far outweighs any dopant atoms we introduce. Even at like the approximate numbers that I know of, if we introduce like 10 raised to 15, 10 raised to 16, 10 raised to 17 atoms in a centimeter cube or volume of centimeter cube of silicon, it like one impurity out of those 10 raised to 18 only displaces one silicon atom out of a million. So purity for silicon will be still insanely high. Okay, so the actual number of silicon atoms in that cubic centimeter is about a million times, like 10 raised to 18 or so. Okay, so what was I saying? Oh yeah, as the dopant quantity concentration keeps on increasing, once we cross 10 raised to 21, it acquires near metal-like properties. Okay, so there are electrons and free holes present in such large quantities that the semiconductor starts behaving like a metal. Okay, and so that's 10 raised to 21 or above. And materials with heavy doping are known as degenerated semiconductors or degenerate semiconductors. Okay. I personally have never worked with a degenerate semiconductor. Nothing of that kind of heavy doping profile. Most of the devices that we use in everyday life is somewhere in the middle, right here. Okay, 10 raised to 17, 10 raised to 18, 19, approximately in that range. All right, that's the last one before. Is it not synced? Okay, there we go. All right, so in metals, insulators, of course, cannot conduct because they don't have any free electrons. Metals have a whole bunch of free electrons. So if you apply an electric field, current starts flowing, the electrons are responding in the direction of the electric field. So current flow is due to only one mechanism, and that is known as field-induced current conduction. Field-induced simply means, in simple terms, applied voltage. Okay, applied voltage. In semiconductors, however, there are two mechanisms for current flow. The first one is the field-induced, meaning you apply an external electric field and your carriers drift in response to that electric field. Okay. Electrons will want to move with the field, holes will want to move against the field. The second one, or the second mechanism for current flow, is introduced due to the gradient that occurs because of the doping profile. So if we take a bunch of atoms and we introduce into our silicon wafer, what's going to happen is the concentration is not going to be uniform. Right near the surface, if this is the surface, and this is going into the wafer, and this is the doping concentration. Doping concentration could be very high near the surface or wherever it's implanted and slowly go down to zero, right? Physical laws govern everything. So if you're introducing a impurity into a material, it's only going to diffuse up to a certain point, not going to go everywhere. So once you introduce these dopant into your semiconductor material, there's a concentration of these atoms or these charge carriers at one spot. And because there is a gradient in the concentration or the doping profile, the charge carriers, because there's a gradient, there's an imbalance in the charge across the profile of that semiconductor material. So in a bid to even out the charge concentration, the charges start moving or diffusing through the material. And so that current is known as the diffusion current. And this occurs only in semiconductor devices, not in metals. Metals, you always have electrons available, and so they drift in response to electric field. Semiconductors, you have drift, and you have diffusion that occurs because of dopant concentration. It's basically like, if you have water or clear liquid and you drop a dye, some sort of colored dye in there, and you'd see that material just diffuse to the water. That's kind of like that. So you but you introduce external dopants into your wafer and it diffuses through the wafer. And one of the parameters, this is known as the Einstein's relationship, basically describes thermal voltage VT is KT over Q. So thermally generated voltage inherent in the semiconductor because of thermal effects. K is a constant, T is the temperature in Kelvin, Q is a constant. So this quantity will come up again and again in many equations down the line. Okay, so it's an important relationship to remember. Okay, so let me go back and let's talk about this law of mass action. Okay, law of mass action. Intrinsically generated electron hole pairs would be N and P. N is equal to P is equal to Ni. So if you multiply N times P, what do you get? Ni square. Remember I said electron hole pairs are generated and then they recombine. And the rate of generation and recombination remains near constant. That's a phenomenon that was observed very early on. Okay, the rate of generation recombination, it's doing the cycle constantly. Even if it's just sitting on the desk, small piece of semiconductor silicon, constantly generating and recombining electrons and holes. So this rate remains near constant, so it's electrically charged neutral. Okay, so electrical charge is neutral. So N times P Ni square governs intrinsic semiconductor as well as extrinsic semiconductors. Okay, so this phenomenon came to be, I mean, not came to be, they studied it. They saw like you're introducing 10^18, 10^19 times impurity atoms in a semiconductor material. Now you have so many negative charges in there. How is the sample still electrically neutral? And so over time, when they did research, performed experiments, they came to know that this phenomenon occurs where when you introduce new dopant atoms into a semiconductor material, the rate of regeneration adjusts so that the electrical charges balance out. Okay, and that law came to be known as the law of mass action. So whether it's intrinsic or a doped extrinsic semiconductor, this equation will always, always, always hold true. Let that sink in for a minute, not a minute, but a few seconds, and then I'll talk about why it happens. And then we have about less than 10 minutes actually to get through our homework. Okay, so N times P, the number of electrons times the number of holes, is always, always equal to Ni square. Now, the reason why this happens is, let's say you have a semiconductor material. My right hand is electrons, left hand is holes. Okay, the numbers are equal. Let's say introduce a whole bunch of donor atoms in here. So now the number of electrons goes up, extrinsically generated electrons. What they discovered was the phenomenon that occurs is because the number of electrons have now increased, a portion of these electrons will jump into the spots that are available. These spots are basically positive charge holes. So when those electrons jump into these holes, the number of holes goes down correspondingly. Again, originally, this is the intrinsic level, electrons and holes. You introduce external electrons in here, number of electrons goes up. At the same time, many of these electrons, not many, some of these electrons jump into the spots that are already present, whether it's due to intrinsic, whether due to another acceptor atom, doesn't matter. They jump into the available holes, and the number of holes start disappearing and the positive charges start going down. And so this phenomenon was found to occur in both N-type, P-type material in all semiconductors. So again, the study of this field is, again, it goes into quantum physics, solid state device physics. Okay. But does everybody understand what I'm trying to say? So the rate of regeneration increases to balance out the charges, right? Electrons jumping into holes is regeneration. So as soon as you have more electrons, the rate of regeneration increases. As regeneration, recombination, sorry. The rate of recombination increases, and because the rate of recombination increases, the number of holes start decreasing until the charges are balanced out. And it's very interesting that this law applies to all semiconductors. It applies to any kind of dopants in any quantity. It'll keep occurring until it's electrically charged neutral. This stable state is also known as equilibrium or thermal equilibrium, meaning at any particular temperature, the rate of generation and recombination always balances out to keep it electrically charged neutral. Okay, and so this is known as equilibrium. And the equation that governs this is known as the charge neutrality equation, which is stated and given in problem number 1. So we'll go over the homework problem in a minute, but take a few seconds to let it sink in, think about it. Let me know if you have any questions. Did all of that make sense? Enough. Okay. Let's go to the homework problem. Okay. Let me do this. I'll do it here. Homework 1. This was question 1, 2, 3, right? At the top of the question, the charge neutrality equation was given. And the charge neutrality equation is given by P, which is the number of positive charges, plus the number of ionized donor atoms will always equal the number of negative charges or electrons plus the number of negatively charged or negatively ionized acceptor atoms. And so if P plus N is equal to N plus NA, then this should equal 0. This is the charge neutrality equation that was given in that problem. All of these atoms, electrons, holes, it's always the number of atoms, number of electrons, number of holes per centimeter cube, per volume. So the book uses density because it's per volume. Okay, so the book uses a subscript of O, but the equation is still the same. I just want to clarify that. It says density of, but the reason it says density is because we're talking about number of atoms per centimeter cube or per meter cube. Makes our job easier. Don't have to convert anything. So all the values are given per meter cube. All right, so in that problem, charge neutrality equation was given, plus this was stated. N times P is equal to Ni square. Now, the reason I assigned this is because we, obviously it's like, how can you assign something before we talk about it in class? The whole reason was like, just to get students to think. The information was provided. It's not an easy topic by any means. Even EE students are not able to do this, without any instruction first. So this was just not to test or assess. I just wanted to see if students were able to like do anything with it. Anyway, so N times P is Ni squared. We just saw how and why that happens. So we can write from here that N is equal to Ni square over P, or we can write P is equal to Ni square over N, right? And that's all we need. That's all we need. So if you're solving for a N-type material, then we want the number of electrons. So we want to get rid of the number of holes, which is this quantity. And if it's a P-type material, then we want to solve for the number of holes. We want to get rid of N. So all we do is we take these and we substitute it into this equation. That's all we do. So I'll show you what we're going to do for questions 1, 2, and 3. I believe question 1 asked you, it gave you ND, NA. ND was given as 0, NA was given as 10 raised to 17. So if ND is 0 and NA is given as 10 raised to 17, what kind of material is this? This was a P-type material. I believe almost everyone got this correct. Well, obviously, we had multiple attempts, but number of donor atoms is 0, acceptor atoms is 10 raised to 17. This P-type material, if it's a P-type material, we want to solve for the number of holes. We want to get rid of N. So we will substitute N is equal to Ni square over P into the charge neutrality equation. And so we obtain, so N is equal to Ni square over P into CNE. And then ND is given at 0. So we can write P plus 0 minus Ni square over P minus Na, negatively charged Na. The plus and minus sign doesn't matter. The book uses minus sign, so I'm using the minus sign on the Na. Otherwise, it doesn't matter. It's just indicator it's an ionized atom. That's all. Now, it's P. I'll multiply the entire equation with P. I get P square minus NAP minus Ni square is equal to 0. Ni square is given. Na is given. You plug those values in. What kind of equation do we have? It's a quadratic equation. Just solve it. B square minus 4AC is greater than 0. So there are two real roots. One will turn out to be positive. The other one is going to turn out to be negative. Obviously, number of electrons or number of holes can never be negative. So positive is the correct answer. And that's it. And once you have that answer, you plug it into, once you have the answer for P, plug it into here. You have the number of electrons. That's question 1, 2, and 3. I'm going to rush. There's about a minute and 15 seconds left. There was question 4, 5, and 6. So 4 through 6 was the opposite. ND was 10 raised to 18 and NA was 10 raised to 17, I believe. I can't remember exactly what. So ND is higher than NA. But in this case, NA is not 0. NA is not 0. So you have to take that into account in your equations. That's the only difference. The methodology and the methods and the equation remain exactly the same. The only difference is it's ND minus NA. Even in the previous equation, it was NA minus ND, but ND was 0, so we didn't have to worry about it. In this case, it's ND minus NA. That's the only difference. This is a N-type material. You solve it using the exact same method that I just outlined. All right. The homework is extended until tomorrow. You have multiple attempts. There is no reason why every student should not obtain full 100% on that homework. If you get stuck, send me an email. I'll be in my office tomorrow. If you need to meet me for 5 minutes or 10 minutes, I'd be available. Just send me an email. Let me know they're coming by, right? So we'll end class here today, and we'll pick up here again on Friday. We'll look at PN junctions. Yes.